Okay, so in last lecture we started looking at regression, topic of regression. We saw basic intuition of regression. We saw Troy example, and today we'll in this lecture we'll see cost function and gradient descent algorithm, which is an optimization algorithm, which is used in machine learning for different algorithm, and in regression we also use gradient descent algorithm to find optimal weights for a line that fits the data. So I'll briefly go through last lecture. So regression is mapping of continuous inputs to continuous output, or the output is real valued. In classification, output is discrete valued. In regression, output is continuous valued. We looked at this example of estimating salary of a person based on experience, and we talked about how we can fit a line to predict salary of a person which is not given in the data. So that is typically problem of regression. We could use regression for a housing problem to predict price of a house. Regression could be used for stock price estimation, and so on and so forth, where output is real valued. Then we looked at the history, why regression is called regression. Because regression in dictionary, when you look at the word regression in the dictionary, it means to return to a previous and less advanced or worse state. So why we use regression, or why we call regression or line fitting regression in machine learning? We looked at this paper from Galton from 1886. It's very interesting paper. I described it a bit, and I ask you guys to download this paper from this link, and you can just read it. It's very interesting history. Um, then we just formalize the problem of regression. Again, we looked at the calculus. We talked about how we can fit a line using least squared error, or squared error as we call it. And the best line, as we describe, will be the one that minimizes the error between line and the data point. So when you are given bunch of data points, best fit line would be a line that is approximates data well, or which is closest to all the points. So that is the best fit line, and regression is all about finding the best fit line. Then this was the intuition, how changing the parameter would affect line. I give you a few examples. So when c equal to 0, so c is one of the parameter, and this is just a matter of notations in some text, in some book. Hypothesis is called as h of theta, and c is theta naught, and m is theta 1. So I use this notation C and M because this is more intuitive, because we know that equation of line is y equal to mx plus c. So I use these notation. But if you have more variables, then using theta would be more intuitive, because then you will have theta 1, theta 2, theta 3, and so on and so forth. So when c equal to 0, it means line passes through a region, and m is the slope of a line. Again, c over here is the y-intercept. So c equal to 1 and m is 0.5, which is very intuitive for us. And from calculus, we know how this parameter would affect line. Um, then we looked at some loss functions, and we talked about sum of squared error, or scared loss as we call it in regression. We use this loss for regression, and we discussed reasons why we use this loss in regression. So this loss can be written like this: if our hypothesis is C, or a constant line, and we solve this, that how we can find a C that best approximates the data. So this was just derivative of squared loss, and we make it equal to 0. So we derivate this equation with respect to C, because we are trying to find value of C which best approximates the data. So after we differentiate it, we make it equal to 0, and we solve it for C, and we find very interesting answer, that C equal to summation of yi over n, which is just an average value of all the data points. So it's a mean value or average value. So if you're given a lot of data points and you just want to pass a constant line means it will have the same input a same output for all the inputs. So you just make find the average of the data point and draw a line. So let's say average is over here, and you just draw a line. So this would be a regression line. It's not a good fit line, but this is a constant line we can find from the data set. And in the same way, if we make our hypothesis equal to mx, so mx means c is 0, and when c is 0, it means line which passes through region. Again, we can just differentiate this sum of squared errors or squared loss. Now, our predicted value is mx. Previously, it was c, now it is mx because c is 0. Again, we differentiate this equation, we make it equal to 0 and solve for m, and we can find value of m like this. So this is the equation of m for a given data set, and we can just plot this line to see how it fits the data. So if this is the data set we are working with, this is the constant line because this is the average value of all the data points. And this is if we find the m slope of a line based on the data set. So this approximates better. So this is the intuition of regression and how we can fit a line. And today we'll formalize a cost function, and we'll see gradient descent optimization algorithm, and we'll fit this cost function and gradient descent algorithm together to have a proper regression algorithm. Again, we are working with the same data set, salary and experience, let's say. And our hypothesis is mx plus c, and we want to choose m and c, which are parameters of model, which best approximates this data set, right? So these are the data set, and green line shows how far it is from the line this is passing. So this green line shows the error, actually magnitude of the error. So formalize. This is our squared error. So y hat over here denotes predicted value, or predicted value comes from as called hypothesis H. Here we are calling it y hat, and yi is actual value given in the data set, and n is total number of sample, and argmin means we are trying to minimize this function because this is a log function. We are trying to minimize m and c parameters in order to find a value which minimizes this value. So we're trying to find m and c which minimizes this function, and y hat is our hypothesis, which is equal to mx plus c, right? And that's why it is written R main m and c, because m and c are parameter and x is input or the data set we have. Right, and we can just write it. This is proper way of writing this cost function. Usually in books, cost function or loss function is denoted by j. So j of mc, this is the cost function. Again, this is the same value argmin mc as I have written over here. Summation over all the data points in the data set. Y hat minus yi. Y hat is predicted value from a regression line. So this is actually predicted value means over here this value is predicted for this data point. So this is loss, this line is incurring. This is just to give you intuition. So this is the loss, sum squared loss, and I have added another term 1 over 2n. And you will see in 10 minutes why I have added 1 over 2n, because this is like mathematical convenience. So 1 over 2n, when we take a derivative, 2 will come over here and 2 and 2 cancel. And actually for cost function, it makes no difference because it's just a scalar which is scaling the value. So mathematically there is no difference, but for convenience we add 1 over 2n, and you'll see why I'm adding 1 over 2n over here. Right. And our aim is to find values of m and c, because argmin, this is our optimization problem. We are trying to find values m and c that minimizes this cost function or squared error function. Right. We are using squared error, you can see. So this is a complete formalization. Our hypothesis is given by mx plus c, and c is theta naught if you just read in book, and m is theta 1, and h of theta x. Parameters are m and c for our model, Cost function, as we described previously, is given by j of mc, which is argmin of j argmin. This is given over here. Our goal is to minimize value of m and c for this function, this error function. And 1 over 2 n is just a mathematical convenience, it's just a scalar which scales this value. Now, before going in deep into mathematics, how we can optimize values using gradient descent, I want to give you some visualization of cost function because it's very important to visualize cost function. To visualize cost function j in 2D, one parameter and one predicted value. So because in 2D it's very intuitive to see. I will show you how we can do it in 3D as well. But initially I will show you in 2D how we can visualize this cost function, and then I will visualize in 3D. So in 2D I will just have one output and one input. So input is given by m, or this parameter m, and I'll plot. So this would be m, and I will plot j of m. So you can just visualize how this cost function looks like, or squared error looks like. So we can set c equal to 0, and we are working with only m parameters. So we are considering line from origin with some slope m. When c equal to 0, it means line is passing through origin. So let's say this is the data set we are working. If input is 1, output is 1. If input is 2, output is 2. If input is 3, then output is 3. We are given this data set. And we just make this hypothesis that m equal to 1. Right? We are working with only one parameter, remember? So we are considering only line which passes through origin. And this is the line which passes through origin. And if m equal to 1, we exactly fit the data point. Right? So m equal to 1, and this is our cost function. So before it was jmc, now it is only jm because we are working with only one parameter, and hypothesis is given by mx. There is no c because c is 0, and which means that we are considering lines which passes through origin only. So when m equal to 1, when m equals to 1, previously this line, there was no error. Remember? So you can just put values over here. Y hat and yi all are same. So this gives all zeros when you put values in this equation, and we will get 0. So cost of m equal to 1 is 0. So j of 1 we can write j of n because it was j of m, and now m is equal to 1. So we can write j of 1 equal to 0. Now this is the second line when m equal to 0.5. So when the 0.5 slope is different and we are inducing some error. So this is the data point. Let's say we are inducing this error over here. We induce error over here, and we are inducing error over here as well. Right? So when m equal to 5, m equal to 0.5, we can calculate loss like this. So you can just see it will be 0.5, 1.1 and 1.5, and it's a squared error, so you put all the values back in this equation to find this answer. Whatever comes over here you divide by 1 over 2n, don't forget that, and n is 3, so it's 1 by 6 over this value, and you will find this answer 0.583. Now this is our third line, which is m equal to 0. When m equal to 0, this is the line which is just parallel to x-axis, and when so we are inducing errors like this when m equal to 0. So initially it would be 1, it would be you can just calculate all the errors. So it would be like 1 square plus 2 square plus 3 square, and this is 1 over 6, 1 over 2n. So this would be 1 over 6 multiplied by 14, and you can get this. So these are the lines, these are the errors which we can calculate using different values of m, and we can just plot it to see how this function looks like. So this is m, and let's say this is cost of m. This is 0. This is 0.5, let's say 1, 1.5, and same over here. So when m is 1, cost is 0. So this is the point. When m is 0.5, cost is 0.5 something over here. And when m is 0, when m is, sorry, the last point should come over here. When m is 0 is 2.3, so something big. And we can just trace this values. You can find something like bowl shape function, and this is convex function, and that's why and remember in last lecture we also discussed why we use sum of squared error, and this is the reason why we use sum of squared error, because we'll find bowl shape function or convex function, and it has very nice mathematical properties because it has only one global extremum, and that's what we wanted to find, because we want to find cost equal to or minimum value something very near to 0, and this is easy to find in this kind of function. So this is the intuition of this cost function. If I plot this using MATLAB, I have MATLAB code as well. I can show you later on. This looks very symmetrical. So this is the cost function when visualized in 2D only. So now it requires 3D to how we can visualize cost in 3D when we have two parameters m and c. Last, this graph or this function was only for one parameter, or in 2D, because one is the input and other is the output. But how we can visualize in 3D? So if you visualize this cost function in 3D, it's again ball shape function, and I'll show you in MATLAB how it looks like. Let me run the code. Let me run the code, and I will show you the screen. Okay, I guess this is visible for you guys. So this is the same cost function plotted in 3D. So this looks very nice, convex function. And if you want to know more about convex function, please reread your calculus books, because it's interesting to know what is convex function. And machine learning, we are looking for convex function for the same reason as is discussed in calculus class. So you can see this is ball shape function in 3D. Here, two parameters are m and c are given over this axis, and this is the cost. So actually the height over here gives the cost value. M and c are two different parameters, and the height of this function is giving value of the cost. So you can just see and visualize that cost function in 3D. So cost function for linear regression will always be bowl shape or convex function. So there is no local minima except for one global. So here you can see there is only one global minima. There are not many valleys and ridges in this function, and this is the property we want to exploit in machine learning. So gradient descent is an optimization algorithm that finds the optimal weights W for m and c. So that was the cost function, but we want to find weights for m and c so that we can find this value. And for that we use gradient descent algorithm, which is an optimization algorithm, and will optimize this cost function which we have formalized previously. It can optimize weights for any general cost function. If there could be cost function in different forms, we are using sum of squared error. There are different lot of loss functions we can use. Gradient descent is a general optimization algorithm, and we can use different cost functions with gradient descent to optimize the cost. So this is algorithm given in kind of pseudocode for a gradient descent algorithm. So input are two parameters of cost function n, m and c, or theta 0 and theta 1, and the output would be values for m and c that minimizes this cost function. So initially, initial weights for M and C would be random values, and usually they are taken as 0, 0 initially. Usually they are initialized as 0, but it could be initialized with random values. And we calculate sum of squared error, SSE is sum of squared error. We'll calculate gradient, and gradient is change in sum of squared error when the weights are changed by a small value from their origin randomly initiated values. This helps move values of W in the direction in which SSE is minimized. This I will explain in next slide as well. But we calculate gradient, and gradient gives tangent to a function on that point, and that gives a change, or that gives an idea where weight should be moved in order to find minima. So either weight has to be added, or weight has to be subtracted with some value to move on that functions in the direction of minimum value. But I will make this point clear in next slides. So we'll initialize weight, we'll find the gradient based on those initial weights. We'll adjust weights based on calculation of gradient, and based on we'll adjust weight, we'll update new weights, and we'll use those new weights in the next iteration to find new SSE. And we'll keep on repeating step 2 and 3 till further adjustments to W doesn't significantly reduce the error, or there is no change in W. So after, let's say, after 2 or 3 iteration, W1 remains equal to W1, so there is no change, we can step over here and we can say that algorithm has converged. Or if the change is not significant, we can stop. So there are different stopping criteria for algorithm, but this is the general idea. So initialize weights of M and C, or theta 1, theta 2, calculate gradient, adjust weights based on those gradient, then use new weights to find again gradient, and keep moving on. So this is general idea of a gradient descent algorithm. And mathematically, this could be written like this. So this is cost function in 3D, and this height is given value of j. M and C are two input parameters, and W over here represents weight. So this could be M, this could be C, this could be theta 1, theta 2. So W is like a general term I have used. So do not confuse with notations with why I'm using W and why I'm not using M or C. So I'll just explain each term. So let's say if this is M, so M equal to M minus alpha. I will explain this alpha. Alpha is learning rate. So if you have, let's say this is our cost function in 2D, and we are over here, and we want to reach at this point, because this is the minimum value of cost. Alpha will tell or dictate how long steps an algorithm should take. If alpha is too big, maybe next stop or step would take algorithm over here, and then it will overshoot. But if alpha is very small, it will take lot of iteration. It will keep on moving on this line slowly, and it will take maybe thousands of iteration to reach this minimum value. So alpha is the step size, or it tells or dictates algorithm how long the step should be, or how big the step should be. So this is learning rate alpha. And this term, again, as we did in last lecture, is the derivative of cost function, and this is the gradient. As in previous slide I was showing you that we will calculate gradient, and this term is dictating gradient, and this tells how big the step, or in which direction we have to move. Let's say if we are over here, so tangent of gradient will give this tangent line which touches at that point with this function, and this tells us if slope is positive, then we have to move in negative direction. I will explain how, because this is negative. But this gives the direction where algorithm has to move, either in this direction or in this direction, right? So again, I will show you in MATLAB. Let me run it once more. Is it visible? This 3D graph?
जी से visible है.
Right. Let me. You can see the steps are coming. This blue stars or statics. So this is how algorithm is moving to find minimum value. I'm not able to. Let me rerun it because I am not able to rotate it. Anyway. Okay, so this is how alpha is small. I have kept alpha small for the visualization purpose, and you can see that algorithm or the weights are moving, so the cost is getting reduced. And we want to reach global minima, which is at the bottom, and this is how this algorithm will keep moving, right? You can see this blue stars. Weights are getting updated in each iteration, and algorithm is moving downhill to find global minimum. Right? This is shown over here in illustration as well. Right? You can see this. Any issue up till now? Okay. So this is the same algorithm I've written only for one parameter m, where alpha is the learning rate and we are differentiating with respect to m, and this is learning rate, right? And now I will explain how this terms dictates where to move. Let's say we initialize algorithm or algorithm is over here. This is the cost and we want to reach, this is aim to find value for m that minimizes this cost. So we need to find derivative which is a tangent at a given point. So tangent, if we are taking derivative, this would be kind of a tangent, this. And as slope is positive, so this is the positive slope and this is the equation. So m equal to m minus alpha plus positive number. So this remains negative. The whole term remains negative because plus minus remains minus. So it means that value of m has to be decreased because we want to move in this direction. Finally, updated value m will be reduced and will move towards function minima. But on the other hand, if value of m is somewhere over here and cost is given by 1.5, let's say over here. And if you take a slope or derivative, so this is a tangent and here we can see that this slope is negative. This slope is negative and this slope is positive. So this is negative slope. And if you put negative over here, so m equal to m minus alpha into negative number, that will make it positive. Negative will make it positive. So it means that we have algorithm has to add values in m to move in this direction. So finally, updated value of m would be m plus alpha into that number or the derivative number will be added and will this function will move towards the minimum in this direction. So if slope is negative, it means that we have to move in this direction. Slope is positive, it means m has to be reduced. If m or slope is negative, it means it has to be added. So this is how this optimization of gradient descent algorithm works. So now this is the effect of alpha as I have shown you before. If alpha is very small, we probably have to iterate it over 1,000 times or 2,000 times or even more to reach, because this alpha is very small. So this is how gradient descent will converge to reach over here. You can see. But if alpha is too large, what could happen? Probably, let's say if algorithm starts over here, and if alpha is too large, the step size is too big, and we want to reach over here, maybe after one iteration it will jump over here, second iteration would be over here, third would be over here, and so on and so forth. So even it will not converge, and in some cases it will diverge and will not find the right correct solution. So this is the problem of finding correct alpha or a learning size. So we have to find a nice balance between a very large value of alpha and very small value of alpha. And this is a very interesting slide I took from Stanford's course, which shows effect of learning rate on accuracy of function, and how good it would be if we use different kinds of alpha. So if alpha is very high, like I showed you in this, loss would increase exponentially. It shows that alpha is very high. And if alpha is let's say it's not very high but high, so it will maybe stuck in some local minima, and it will not converge to a good solution. And if alpha is low learning, if alpha is very small like this, it will take many epochs, many iterations, maybe to find like this. But if you find a good learning rate, we can very quickly reach best value, let's say best values over here. We can very quickly reach over here. So this is the effect of a learning rate on gradient descent algorithm. So I propose to stop over here, and in next lecture we'll put regression, sum of squared error, loss error with gradient descent together to find values of m and c, which minimizes that cost function. So see you next time. Thank you.